We have a lot more students. I'm going to see if some people can't start the presentations in October. I know some people have already got presentations. Okay? Some people have already got presentations. Some students will do...
What is the presentation?
The presentation is on anything you want.
But by anything we want, is it like...
Well, I would hope it would be something technical on materials.
So
okay?
It's technical on any material?
Any material you want. I had one student do fancy doorknobs, antique doorknobs. Okay, and how they were cast or wrought or whatever. I had another student do sailboat mast, composite sailboat mast. They were interested in sailing, right? Another one do flying buttresses in the architecture of old cathedrals and things like that, okay? I find if you get to pick a topic you are interested in, you will do a better job. Duh, okay, okay. Now, some people have come in and done a presentation on their thesis, okay, which I don't care. Some of them have done presentations on other courses, presentations they had to do for another course. I don't care, okay. I do double dipping all the time, okay. Yeah, so General Motors does double dipping. They'll advertise one car here and they'll advertise another car over here, which is basically the same car. What's the difference between a Chevy Suburban and a Cadillac Escalade and a GMC Yukon other than price and a few features, right? The body metal is all the same, right? So anyway, I have to have something. The Institute says I have to have something to evaluate each student individually. I can't give a class grade. Okay? It's not my rule, you know. I work here, okay? I have to follow some of the rules. Not very many, but I have to follow some. Okay, anyway. So the presentations, I hope to finish up lectures by mid-October, and sometime soon after that I'm hoping that some people will already have presentations, will be ready to start doing presentations. Because as the term wears on, see, we're going to have to do about 10 to 15 days of presentations to get through all 40 students, okay? Because I can only do about 10 presentations a day. Presentations should not be more than 10 PowerPoint slides. In fact, it doesn't even have to be PowerPoint. If you're really good, you don't need slides, okay? But none of you are really good yet at giving presentations. You still need that crutch of slides, just like me, okay? Lester Thoreau could give talks and get $30,000 an hour, and he didn't have any slides, but he had lots of catchy little phrases, okay? So, President Obama very infrequently uses PowerPoint, okay? Okay. If you want to see PowerPoint in all its glory, there's an article by Edward Tufte, who's this guy, used to be at Yale, and he teaches communication, and he had Auto Content Wizard of PowerPoint do the Gettysburg Address. You want to see how PowerPoint can take a great piece of English literature and turn it into absolute junk, okay? PowerPoint is not there to just read your presentation. If I wanted to read your presentation, I could have you email it to me. We wouldn't have to have you make a presentation. PowerPoint should be there to show graphs and pictures and visuals that are necessary to convey the information. If you could convey the information without PowerPoint, it would be a much better presentation because people will focus on you and not the slides. Okay? But that's another story. Does that answer your question about the presentation? So you have to come to these 24 hours of lectures, 12 of mine, 12 of Dr. Belmar, and then you have to pick another module out of these 10 or 12 modules that I've lectured on in the last 3 or 4 years, which include casting, codes and standards. Dr. Belmar did life assessment. I did deformation processing, which is forging and rolling. I do welding. There's a number of different things. But you're supposed to pick another 12 lectures and watch them, okay? and hopefully be entertained. And hopefully you won't hear all the same stories, okay? Hopefully I have enough stories to talk for an hour in stories. Any other questions? If not, then let's begin. This actually is just, I'm not going to go through this, but we will talk about aluminum in a little bit more detail. And this is something I just came across last week in a metallurgical magazine, which is just going down the history of different metals. And for most of the past 6 or 7 months, they've been doing steels. Now they're starting to do part 1 of aluminum. And here's Charles Martin Hall in 1905 at age 42. When he was 22 years old, he and Paul Héroult, who was in France, both independently invented the process we still use today to make aluminum. Héroult beat Hall to the patent office, and you read this story and find out how Héroult actually won the battle because he could show that he reduced it to practice, not in April when Hall filed his patent in June or July. Héroult had filed one in April for the exact same thing, and the patent office says, oh, yeah, Héroult has priority. But then Charles Martin Hall showed that he had actually reduced it to practice in February. And so he won in the courts and founded a company called Pittsburgh Reduction Company that eventually was funded by the Mellons of Mellon Bank and later became Alcoa, the largest aluminum company in the world by far, which was broken up into Alcan by the trust busters in the 1910s and 20s or whatever. And Héroult started a company in France called Péchiney, which is still in existence. Alcoa is still in existence, so far as that goes. Anyway, you can read about it. The story there is sort of learn a little bit about patent priorities, I guess, and just learn something about aluminum. And you get a nice picture of these guys, Andrew Mellon, Arthur Vining Davis. Okay, so other people come in. Have you had any questions? If not, I'm going to actually lecture about what I've been prepared to lecture the last 3 days that we've had class. If not, okay. So the theme from last Tuesday, and actually the day before, is there's active competition among materials. Okay, and we're going to go over that. The schedule is I'll be here Monday and Thursday this week. I'll be out of town the next 2 days. Dr. Belmore will be here the other 3 days, and he and I are going to be discussing what will be in the next week. I may have to give you 2 days off on Tuesday and Wednesday of next week because it's possible that both of us will be out of town. So you can watch those other videos, right? You can start watching your other module. Okay, so what's the competition? I've talked about conveying water. I put this up several times already. I've simplified it or made it more complex in some ways. If you're conveying water, I mean moving water from the stream to your home, not just carrying it. You could carry it. Someone put skins up, okay? I guess I could put skins. You can carry it in skins. You can carry it in ceramic pots. But if you're conveying it in a pipe or a trough, you can make a wood trough. You can make stone and mortar, concrete pipe, lead pipe. So here we're back in the 1770s. Concrete pipe, the Romans had aqueducts and things like that. Well, not as pipe, but as troughs. Galvanized steel came along in the 20th century. Cast iron came along actually at the beginning of the 20th century as we learned things like how to do centrifugal casting of steel. Centrifugal casting is you just have a refractory mold that's in just a cylinder. It's got a big long hole, and you pour the material in and spin it around as you're doing it, and you can use centrifugal force to hold the material up against the mold until it solidifies, and you end up with a cast iron pipe. We've been doing that for 100 years. Okay. Reinforced concrete. A lot of the pipes, you go along the highway and you see them putting in some 10-foot or 20-foot diameter pipe in some cases, and it looks like a big concrete pipe. It is, except it's got steel wire mesh inside it to give it strength, because a big concrete pipe 10 feet in diameter would break under its own weight if you sat on, well, not just under its own weight, but if you sat on it. Okay, great big circle, it's thin walled. It's brittle material, and so you need something to help strengthen it. So it's really a composite reinforced concrete. Concrete lined cast iron. Well, a lot of the cast iron we put in 100 years ago, and there's a lot of that pipe out there, it's been doing pretty well for 100 years. And the reason is, if it had been steel, steel would corrode within 30 or 40 years. Okay? Remember, that's the Achilles heel of steel. Cast iron has got like 3% silicon, and it forms this glassy silicon dioxide layer. It is glass, basically, on the surface. And that protects it from corrosion for a while. But after about 100 years, depending on the quality of the water, that starts to break down too. And so what they've been doing, rather than dig up all these water pipes, and Boston is an old city that actually started putting water pipes in 100 years ago, and they have hundreds of miles of cast iron pipe water mains all through the city of Boston, and towns here around about once a year or twice a year, you'll see some big ad in the paper where a 8-inch or 12-inch water main burst, and you have this big flood, and floods downtown and does a few $1 million worth of damage. And that's because these things are 100 years old now, or because some contractor comes along with a backhoe and whacks it, and cast iron's not very strong. It's somewhat brittle. But one of the things they've been doing to extend the life, and they've been doing this for 30 or 40 years, is they have machines that will run down that pipe buried in the ground and coat the inside with about a ½ inch of concrete. Okay, it's just a machine that you pump the concrete in, you shut down the line, you drain it, and then you put this machine in there that will run down there and just automatically trowel on a little layer of concrete. Because concrete has excellent corrosion resistance from water, against water, and will last a long time. So now we're using concrete lined cast iron. We also have people do plastic lined cast iron. They take a great big balloon, if you will, and they turn it inside out, inside the pipe. And some of these are polymers that they then go in and use a big ultraviolet light to go in there to harden the polymer in place. You know, take this big long, you know, the balloons that you make little dogs out of and stuff, right? Take a great big long balloon like that, turn it inside out, and line the inside of the pipe, then send a big light down there with ultraviolet light to cure it in place so it hardens up, and you got a plastic pipe, and you still have you haven't moved your cast iron or anything like that. Now that's not the best in class among all these things. We still use, well, lead pipe's about the only thing that we don't use anymore. Okay, best in class would be gold or titanium. We don't use those most of the time for obvious reasons. In the case of gold, it's too expensive. In the case of titanium, we do use titanium pipe, but not to convey water in heat exchangers where we may have 10,000 little thin wall tubes. We used to make it out of brass 30 years ago. Today we make them out of titanium because they have excellent corrosion resistance. So if I'm going to put in a heat exchanger or some great big electrical utility, and I want it to last for 50 years rather than 15 years, I can make it out of titanium. I will make it out of titanium. It's a very big business to use thin titanium tubes in heat exchangers. Titanium just doesn't corrode in water. Okay, it doesn't pit. It's just a little pricey. And you have to learn how to weld it and things like that. The worst I've ever heard of was back when the price of copper, did I even put copper on here? Yeah, I forgot to write it down. So we'll put it in here somewhere, okay? We've been using copper pipe since the 1940s in large volumes. That's what you have in most of your homes. Or maybe I didn't. We also use plastic pipe, PEX, which I already talked about. I guess I was thinking about something else. Anyway, we have copper and plastic. Copper came in the 1940s in a big way. Plastic, this PEX tubing that I think I passed around, came in the 1990s, early 1990s. Been around for about 25 years now. And copper was expensive. When copper got even more expensive in the 1970s, Allegheny Aluminum Steel says, stainless steel is very good, and we can make it thin wall and we can make it cheaper, but we have to have something that the plumber can solder to. So that's another material property in the material selection. You can't solder to titanium. It's got this protective oxide. There is no flux that will eat away the titanium oxide solder, okay, titanium oxide. So you can't solder to a titanium pipe. But stainless steel, it's got a chromium oxide. You can solder it, but you have to use pretty aggressive chlorides, which can pit the stainless steel. So they decided, we'll just plate the copper. We'll put copper plate on the outside, and now you can solder to it just like you do a copper pipe. Well, they did that, and they did tests before they put it in service. They had these loops running water through the thing in the laboratory, had no corrosion on the inside, put it in a building in Florida 40-some years ago. Actually, when I was a student, my thesis advisor got involved in this. 40-story high-rise down in Florida, right on the ocean. And within a year, they had a sprinkler system, because you put a noble metal on top of a less noble metal. In this case, copper is more noble than stainless. You get pitting corrosion right through the holes in the copper plate. And there will always be some little holes in that copper plate. I was able to take, back when I was a student or whatever, maybe I was an assistant professor, I was able to take some of this material, stainless steel pipe that had been plated with copper, and put it in 100 part per million tap water, basically, and put it in hot water, and put it in half a glass of that water, and perforate it in 24 hours. Just make a sprinkler system, just pit right through, because the copper corrosion, or the copper becomes the cathode, that little hole in the copper becomes the anode, goes right through that stainless steel, just like a magnifying, like burning ants on the sidewalk with a magnifying glass, right? Or if you don't like to burn ants, if you're burning leaves. Don't you remember doing that as a kid? Taking a magnifier and focus all that corrosive current right on the pit.
Why didn't they see it in the test?
Pardon me?
Why didn't they see it in the test?
Because they didn't do an external test. This was in the laboratory. They ran water on the inside and said, oh, the stainless steel is good. They didn't look, and they didn't do it outdoors and let it rain on it and everything else, particularly in a marine environment like the coast of Florida. A little chloride, stainless steel hates chlorides. So they didn't see it. So you got to be careful when you do some tests. And they built lots of buildings with this stuff before, they started getting the lawsuits. And they yanked it off the market within 3 or 4 years, where they paid tens or hundreds of millions of dollars in damages to people who had to replumb their whole buildings, okay? Because they didn't look at external corrosion. Usually inside a house, you don't think that you're going to get a lot of external corrosion on your pipe, okay? It's indoors, right? Well, it is, except humid. In Florida, it does get humid, and the humidity's got chlorides, and just didn't work, okay? Might have worked in Arizona, okay? I don't know if they, might still be some homes in Arizona that have it, okay? But there's all kinds of problems. I don't think I told you the problem about, did I tell you the problem about polyformaldehyde? DuPont in 1958 came out with this wonderful material, easily injection moldable polymer. It's called polyformaldehyde. If you know formaldehyde's what's CH2O. It's one of the most basic types of chemical compounds. And they learned to polymerize it. 10 KSI strength, which for a plastic is really good strength. Easy to injection mold, and they said this is the plumbing material of the future. And they tested it in over 200 different solvents. And they published this paper in 1958, and they gave it the trade name of Delrin. Okay, Delrin plastic. If you look up Delrin, you Google Delrin right now, at least a few years ago, you'd see that they're still selling it, and they still say it's corrosion resistant in a lot of applications. But it turns out within 3 or 4 years, some Germans did a study and told them that there was one solvent they had not tested in the laboratory for this great new plumbing material, and that was water. They tested gasoline and oils and all these methylene chloride, and Delrin resists them all. But it turns out if you have 5 parts per million chlorine, which is sort of what you get if you condense the air in Cambridge, Massachusetts, you'll get 5 parts per million chlorine in the humidity from Cambridge. It corrodes, it stress corrosion cracks. And so for the next 20 years, we had exploding toilets. They made the little water closet valves out of these things, and the thing would just fall apart. Particularly if people put the, you know, the little blue things in the water closet to try to sterilize the, you know, those are like 10% chlorine. They make things 10% chlorine, and they just deteriorate these things by stress corrosion and cracking. And when it would break and the valve would come loose, you get a jet of 60 psi water hitting the top of the water closet, and people would be sitting there watching TV in their family room, and they'd hear crash, and they go in and they see water shooting up into the ceiling of their bathroom, and they call it the exploding toilet. It wasn't exploding. There was no explosion. There was no contained, what was a contained pressure. It was knocking the tops of the water closets off, and their ceramics would fall to the ground. They hear a big crash, and they say, "Oh, it's an explosion." Okay, it was a problem, but eventually eventually Host Celanese paid a $900 billion class action trust fund to help fix these things, and DuPont did something larger, but it was confidential. They probably paid $1 billion or $1.5 billion to have, you know, make it so people could take these things out of their house. And a similar type of thing with polybutylene for plastic fittings and things. So you got to be careful when you introduce a brand new material into some commodity product to make sure you've thought about all the important things. Any questions on that? I'd already talked to you about competition for water bottles, or you know, bottles, whether it's metal or plastic or ceramic or aluminum cans or whatever, and we still have that competition so far as that goes. But there's another one, and this is conveying gas, and this is one that I'll talk about because I've been involved in it. It turns out the first thing to convey gas, the first reason we wanted to convey gas was around 1800. We wanted to have people learn they could take coal and water and cook them together in a oxygen deficient environment and generate what's called water gas. Just heat up coal in a container, drop water, drip water on it, and the carbon will reduce the H2O to hydrogen, carbon monoxide, and you'll have, by your thermodynamics, CO2 and water. So you have four species in the gas phase: carbon dioxide, carbon monoxide, hydrogen, and water. Okay, and it's a great formula. You know, I had to do it as a sophomore in thermodynamics class in like the second or third week to calculate the water-gas reaction under different conditions. And then when I was teaching 30 years ago, I made the sophomores do it myself. Okay, well, why do they want to do it? They want to have street lights. It was dark in downtown Boston, okay, at night, and there was muggers and, you know, anyway. So the first thing they did, they just took wooden logs and they gun drilled them. What's gun drilling? Did I ask you anybody about gun drilling before? Gun drilling is, has anyone ever drilled a deep hole in a piece of metal and you find the drill is not stiff enough and it tends to walk in one corner and you end up not drilling straight down the pipe, you actually can come out the side because the thing bends? We can get around that by gun drilling. They call it gun drilling. This is how they made rifle barrels in the old days. If you spin the thing you want to drill the hole in opposite to the direction you spin the drill, you actually can get a nice straight cut. And it'll go much deeper. You can make a nice long barrel. And in fact, how many of you can do that? Move in opposite directions? I spent most of the senior year in high school learning to do that. I can do figure eights. Okay? Try it. Like I said, I'd be sitting there in class and doing this, and the teachers would look at me. Anyway, I didn't have anything else to do in class in high school. Anyway, so they used wood and they gun drilled it. And they put it in the streets of Boston. They put some tar or something around the joints, and they'd convey gas down the street and have street lights at night. And they had a guy go along and he would light the lights, you know, when it get at dusk, and he'd, I don't know, midnight or whatever, come and shut them off or whatever. Then they got to cast iron, and here's a picture down at the, what used to be Boston Gas, it's probably N-Star or something like that now. I took this picture about 25 years ago when I was working on a job for Boston Gas. And here's a pipe which they took out of, you can't read it, it's sitting there, but 1836. This was a gas pipe on 8-inch, 6-inch cast iron pipe, Sheaf Street in Boston, Massachusetts. When they were doing other work in the 1900s, they came across this pipe, this joint. There's a picture from the side, not a great picture from the side. They just take that cast iron fitting and they stick a bunch of rope and oakum, and which is sort of a tar type stuff. Here's another one with a bell and spigot joint, okay, in cast iron. Here's there's the bell and spigot joint. Here's one undated. And this stuff's been in the ground, and this is the end view of that. It's just a big pipe with little pipes and a bunch of gunk in between. These things have been in the ground for 150 years when they were doing other construction in Boston and dug them up, sort of like archaeological dig or something. They would find this stuff in the street. Well, and that was fine. Cast iron will last for a long time, but they learned to improve things, and they went to, what else did they go to? They went to they had cast iron. They went to steel in the 1890s when they learned to weld steel. Andrew Carnegie had come along. He had learned to make steel cheaply. And then they learned to do welding of long lengths of steel, and now we have black iron pipe, if you want to pass that around. There's a piece of black iron pipe, okay? Go to the hardware store, that little nipple probably cost 80 cents at the hardware store. Problem with steel, cast iron might last for 150 years, and pit some. Steel will last for 30 or 40 years. Most of the gas piping in Boston is held together by the clay in the soil, okay? I didn't tell you a story of 25 years ago when I had a leak in a water pipe in front of my house. My house is 85 years old, I think I said that. My neighbor comes by at 7 o'clock Sunday morning and wakes us up, and he says, "Oh, you got water bubbling up next to the sidewalk in front of your house." And sure enough, I go look, and you can see this little bubbling stream, you know, a little fountain of water 2 or 3 inches high. And it turns out that's where they put the water box, the valve between the town's water in the street and the stuff going into my house. So I called up the water department, and by 10 o'clock they had a backhoe out there, and they were digging. They had planted a tree there in the 1930s, and the roots of the tree had finally gotten in there and moved the thing aside, and corrosion of the steel and everything. The water pipe had broken. Well, I'm sitting there watching them dig this hole in front of my house in the street, and all of a sudden, as I'm watching, I could smell gas. And right then, the Boston gas truck comes up. I thought, oh, how do they know to do that? And then I noticed the guy in the backhoe jumps out of the backhoe, takes some gum out of his mouth, jumps in a hole, and sticks the gum on a hole in the pipe, the gas pipe that was next to the water pipe. I said, how'd you guys know to call the gas company? He said, we always do, because whenever we start moving the dirt around, we always uncover the holes in the gas pipes. We're leaking gas all the time, and they have to go around once a year, and they put these little probes in the ground, and they go sniffing for gas to find the leaks. This is all over the country. We got pipes that were put in the 1920s and 30s, and there are steel pipes that are leaking gas in the ground, okay? We have steel pipes with water, and they're leaking water in the ground, but people don't get as worried about leaking water as they do gas, okay? There have been cases where homes have blown up. We started using plastic pipes in the 1980s because the gas companies realized this was getting a little expensive, and so the Gas Association started working on polyethylene pipe. This is a welded polyethylene pipe. This would be a distribution pipe. One of the cheapest plastics you can get, and doesn't corrode. And it's got a yellow stripe on it because yellow means fuel gas, okay? So anybody sees that pipe, any contractor or construction worker sees a pipe like that with the yellow stripe, they know there's fuel gas inside. Don't mess with the fuel gas unless you like to have a big explosion. Okay, so there was competition for that. We still convey gas today in steel when we need high pressure. They're talking about the pipelines now from Alaska or from Canada to bring gas down to the United States, except we don't need it because of fracking now. But they're talking about taking pipelines that used to run in one direction, and now they're going to reverse the flow in the other direction, because we used to be shipping gas from Texas to the Northeast. Now we got all this gas in Pennsylvania through the Marcellus Shale where they're fracking, and they want to ship it to other parts of the country. So they're actually shutting down pipelines that were running up to the Northeast, and now they're taking it from the Northeast and running it to other parts of the country. But the steel, they still use steel pipes, but they're using 2,000 PSI pressures in some of these cases for these gas pipelines. And at 2,000 PSI and a 42-inch diameter pipe, you got to have the strength of a steel wall 3/4 of an inch thick. And what do? Well, when you have an investment like that, which is a multi-billion-dollar investment, you protect it with an impressed current, an electric current, or anodes of magnesium, aluminum, or zinc buried in the ground. You make the pipeline cathodic so it won't corrode. I've seen pipes come out of the ground that are 50 years old, and if they've been adequately cathodically protected, they look like they're almost new, except for having some dirt on them. No pits, no corrosion. It's what we do on ships, okay? Anybody live in an area, or your parents have a boat, it's got a metal on the hull or something, and they have to put, I'm getting a nod back there, okay? They go out and about every couple of years, they put new zinc anodes on there. They just bolt these things to the hull, and the zinc corrodes and protects the steel screws or other things, okay? The Navy does this. On nuclear submarines, they actually use the electricity generated, and they have electric current that makes the hull of the ship cathodic, okay? And they have the little electrodes on the outside. And so they try to increase the life of the ship that way. So in the 1980s, we had steel for years. If it's big, heavy stuff, but it's little black iron pipe like this stuff, can't really afford to cathodically protect it. What do? They paint it with lacquer, okay, clear lacquer. Plastic came in the 1980s. That was great. Copper from the 1940s, when you got to bury things in soil, like a pipe from a propane tank. Might be buried, the pipe might be propane tanks out in the backyard in the rural areas, and they pipe it to the home, and it might be copper pipe because steel just will corrode. Then in the 1990s, the Gas Association was looking for some new way to promote the use of gas, and they wanted a cheaper way than cathodic protection, and so they came up with actually this first. This is what's called corrugated stainless steel tubing. It's got, well, I'll pass it around. It's got I should have cut a piece off. Anyway, when it comes around, it's got a yellow polyethylene jacket. Yellow because it means fuel gas, okay? And it's got 10 mil corrugated stainless steel. You can bend this, it's flexible. A plumber can put this in a house nowadays in one day, as opposed to taking black iron pipe, which he has to cut to length and thread. It takes 3 days to install a house. So now everybody's got, you know, gas fireplaces in the family room, in the master bedroom. They got a gas grill out on the porch, okay, outdoors. Used to be 1 or 2 appliances. Might have a dryer, might have a stove that was run by gas in a home 30 years ago. Today, there might be 10 different appliances in a home that are run on gas because it's cheap. Even though this stuff costs like $5 a foot, these folks are making a fortune off this stuff. Okay, and you have to use special fittings, which are similarly expensive. Replaced a lot of the black iron pipe. The problem is lightning. First started selling it big time in 1997. By late 1998, they started getting complaints of fires. And by February of 1998, they knew for certain it was something had to do with lightning. And by 2000 or so, they knew for sure they were getting perforation. Let me see if I can turn this on. So I see a little hole there. Okay. So lightning comes, storm comes by, hits your house. Here's the hole. Okay. perforates the tube, and you got a blowtorch shooting out of the wall inside your house. Houses tend to burn down, a couple hundred a year. Okay, one guy got killed in Texas. Okay, because of this. They came up with better materials. This is a slightly conductive. Actually, it's basically just, I think it's just polyethylene with carbon black in it, yellow lettering because it's fuel gas. This is actually a better product. It's got 2 layers of conductive plastic. Like I say, I think it just added carbon black, and a layer of aluminum. That yellow pipe, it'll take 1/10 of a coulomb to perforate the stainless steel in that. An average lightning strike has 5 coulombs of energy. So 1/50th the energy of an average lightning strike will perforate the yellow stuff. That stuff that you've got takes about 5 coulombs. This stuff will take 80 coulombs. Just don't get hit by a second lightning bolt in the same spot, which actually does occur fairly often. That's another story. So competition among these materials, so far as that goes. Any questions? We finished competition among materials. And you could take anything else. I mean, I could take fasteners. I could take desk. Okay. I mean, in fact, if someone's looking for a project and you want to do a topic on that, okay, and you like desk, okay, hey, the first desks were probably made out of stone. You know, the next one was made out of wood. They still make them out of wood. Some of them are really nice, okay, made out of wood nowadays, and really fancy. Then they made them out of metal. And I guess they make them out of plastic. They certainly make plastic lawn chairs. They got this type of junk, you know, chair, right? You can take almost any common product, and you can think about it through the ages, and you can see the competition of different materials for these things, okay? And most of these things, it's just a matter of cost and availability. That CSST is more expensive just for the pipe, but the installation cost of doing it 1/3 the time, you get that money back. Unless you have to put in a $5,000 lightning protection system on your house, which you should do. It turns out the National Fire Protection Association down here in Quincy, Massachusetts is a voluntary organization that does voluntary standards. Many of those standards which have been adopted by the government, various governments. There's NFPA 780, which is the standard for installation of lightning protection systems, okay? Who taught us about lightning rods and lightning protection systems? One of our first great scientists in the United States, Ben Franklin, okay? 1756. He got out there and he didn't know he could have electrocuted himself by running a wire up there to a kite, but somehow he had some sort of ground wire somewhere. Probably didn't understand it all. He was the one, the reason why does an electron have a negative charge? Well, actually, why does current go the opposite direction of the electrons in electricity? Because Ben Franklin thought that it was positive charges that carried the current, not negative charges. So he didn't have a way of knowing. He just said, okay, we'll assume it's positive. Anyway, NFPA 780 is the standard for if you're going to put a lightning protection system in your house. And if you look in this, you'll find material requirements for the lightning rods and terminals and things like that. In the United States and most of North America, we have 2 materials, copper and aluminum. Good corrosion resistance for both of them in the atmosphere. They have to be 1/2-inch diameter aluminum. This would be tubing, right? No, air terminal solid. 3/8 inch diameter copper, 1/2-inch aluminum. Why the difference? Copper's got better electrical conductivity than aluminum. Okay, lower electrical resistance, and therefore you don't need as much of it, but it's more expensive. You can use either one, and they got different things for bonding conductors, main conductors, and stuff. You can only use copper and aluminum in the United States. The International Electrical Code, you can use stainless steel, galvanized steel, lots of different things. But in the United States, there's only 2 that are really approved by the NFPA. Okay, that's not, the other things won't work, but they tend to corrode over time. You put in a lightning protection system today, you're going to have to pay a fair amount of money because copper is kind of pricey, and aluminum, you got to do some maintenance on those joints because they can develop resistance and stuff. You have to have really good electrical connections and stuff. The guy who's chair of this thing now, I think he's probably listed in here, John Tobias, U.S. Department of the Army. Okay, so John, and actually the guy who used to be is Mitch Guthrie. Is Mitch on here? Mitch Guthrie, okay, consulting engineer from North Carolina. Anyway, I know both these guys. John Tobias, why is the Army interested in lightning protection? They've had a few ammo dumps go in a lightning storm over the years. Get a nice lightning bolt right through your ammo, and all of a sudden you don't have any ammo left. Not a good thing in a war. Not a good thing if you're anywhere near the ammo dump. It's a bad day. So that's why they're interested in it. Any questions on competition among materials? Like I said, someone could pick a presentation topic on competition of materials. Keep it simple, okay, on the presentations. Don't be too broad. Don't say, I'm going to do competition of materials in automobiles. Well, that's a little broad, okay? Something like chairs would be a lot simpler, okay? Four-legged chairs? Whatever, okay? Narrow it down. You've only got about 10 slides if you're going to do it in 10 minutes. And that's what you've got. 10 minutes. After 12 minutes, I will come up and stand in front of you and start asking for questions if you're not done. Okay. And then we're going to talk about each one of them. That's why we can only get 3 of them done in a day. So now I want to talk about materials have limitations. And the reason they have limitations is because of the strength of the chemical bond. We do not have chemical bonds that have all kinds of possible strengths, okay? If we go back to your freshman chemistry, hopefully you got this in, whether you took it in the chemistry department or course 3 as your freshman requirement, or if you're a graduate student, you saw it somewhere. This is the energy versus distance in angstroms for a chemical bond, okay? You have a repulsive force and you have an attractive force. This is what's called the Lennard-Jones potential, where the repulsive force goes as the 12th power and the attractive force goes as the 6th power of the radius. And the net is this red curve, and at this low point you have the equilibrium, the lowest energy. If you took thermodynamics, you know things tend to like to go to the lowest energy state, and you'll get your equilibrium distance of separation, which in this case is about 3.7 angstroms, 0.37 nanometers. And there is some, in another plot of the Lennard-Jones potential, there's some energy of the bond, which in thermodynamics we deal with all the time. And there is, I don't know what sigma is. Who knows? Just got it off the web. But if I take that and I differentiate that, energy differentiated with distance is a force. You should have learned that in freshman physics, okay? Wherever you were, okay? So here's the Lennard-Jones potential. The total energy, if I differentiate that, it crosses 0 at the minimum, and I get some curve that looks like this. And this is the force, the electrostatic force between two atoms. This is an attractive force, this is a repulsive force. The slope of this, the slope of the force versus distance is known as the modulus of the material. You've probably heard about Young's modulus, okay? Young's modulus is related to the curvature of the energy. The second derivative of energy is the modulus of the material. So if I take something that has a very strong bond like tungsten, or a carbon-carbon bond in diamond, which is one of the strongest bonds. The strongest bond, I was once corrected by a chemist, the strongest bond is a silicon-oxygen bond like in silicone polymers, okay? Slightly stronger, but all around 3 electron volts per atom, okay? So in any case, it's the curvature of the energy curve, it's the slope of the derivative of the energy curve. So this is the second derivative, is the modulus of the material. And there's only there's a limit to the strength of chemical bonds, about 3 electron volts per atom, which is like 400,000 kilojoules per mole. So the modulus of most things is no more. Steel's about 30 million, but molybdenum alloys and tungsten alloys are close to 60 million. They have double the modulus of steel. Diamond is actually 150 million, but the problem with diamond is it's very hard to get it in long lengths, big diameters and things like that as a structural material. It's a structural material as a grinding material, but in terms of trying to build a tree fort out of it, nah, forget it. You know, it's not going to work. You can't go to Home Depot and buy diamond in the big 2x4 sizes, so far as that goes. Okay. If I look in Ashby's second edition of Engineering Materials, he's got a table, diamond, 1,000,000 giganewtons per square meter, which is gigapascals. If I look down here, steel is 200, so 5 times 30 million is 150 million. Molybdenum is here around 400, tungsten is around 400. We have all these other silicon carbide, tungsten carbide, boron, tungsten alloys, alumina, sapphire. You know, they have higher modulus. Why do we need higher modulus? When do we need higher modulus? When we want to make something stiff. Okay, so a number of years ago, I was consulting for a division of Johnson & Johnson, and this is when arthroscopic knee surgery was big. Where these, instead of, when I was your age, I have a torn cartilage in my left knee. Actually, I have one. I matched it a few years ago with one in my right knee. And if I wanted to get an operation to repair that cartilage, when it happened to me in the late 1960s, I had that torn cartilage, they would have to lay your whole knee open to get in there. And you would be in a cast for 6 months. You'd be on crutches for a year. And I decided I could live with a torn cartilage. Okay? I can hear it click even today. Get my head down there near my knee, move my knee back and forth. I can hear the cartilage click in there. I can even feel it sometimes. But then they, in the 1980s and stuff, they started doing, they called arthroscopic surgery, where they put a little slit about 1 inch long, and they go in there with a little tool with just the little nippers. I used to do failures on these things all the time. Call it rongeur, R-O-N-G-E-U-R, and they just eat away and take out little pieces of cartilage until they could remove it in little bits. And they, 2 days you're out of the hospital, no crutches. You know, well, actually you might be on crutches for a week or two, but then, you know, within a month you're back walking around and no clicking in your knee or anything like that. Okay. So you can have your cartilage removed. Nowadays they can give you artificial knees and all kinds of other things. But the problem was they wanted to get smaller and smaller tools, and they had to be longer and slenderer. Okay? Well, what happens if you make something nice and slender and has low modulus? It flexes. Okay? Well, they were trying to make a tool that would nibble at your cartilage, okay, and cut it away, eat it away mechanically. And so they came to me and they said, okay, what do we do? Well, I said, well, there's 2 ways to affect the stiffness of something. One is a material way, and that's going to a stiffer material that has a stronger chemical bond. And there's only a few materials that are above the stainless steel they were using. Stainless steel is around 200, and there's very few materials in here that are much stiffer. Now, another way to get something stiffer is to take it and turn it into a tube. Okay, this is polyethylene. It's not in tubular form. This is a tube, and it's stiffer because it has a geometric stiffness. Okay, so you mechanical engineers, you work on geometry to get stiffness. Materials engineers like to pick a better material, but there are limits to the materials we can have. So I told them that what they could make their tools out of would be, if you look on this list for material selection, alumina, sapphire. I said, why don't you make sapphire tools? Okay, you could buy sapphire for a couple of bucks a cubic inch nowadays. And not only that, you could color it with a little chromium and it would be red. And what do we call that red sapphire? Ruby. Okay, can you imagine what you could charge a surgeon for a ruby instrument? And they would pay. Well, they're so conceited, okay? They will pay for anything, okay? I have a ruby instrument, do you? Okay? If you want to get into it, you know, you can color them so they're green, and if you use the right ceramic, you call them emerald, okay? You could color code your instruments, which the nurses would love. You could, hand me the orange one, okay? Anyway, very good for corrosion resistance. And talk about sharp, they would keep their sharpness. Only problem is you have to machine them with diamond tools. They didn't like my idea. They never did it, okay? But I know that I could have made rongeurs out of sapphire that would have worked really well. There are limits to these materials. It turns out this is Ashby's plot, a linear plot. Here's diamond at the top, and here's your metals, here's your ceramics, here's your polymers. Look where polymers are not very stiff at all. And here are your composites, which are somewhere in between the two of these. However, just because they're not very stiff doesn't mean there aren't times when you like to have a lower modulus. So here's a little article from March of this year that Tufts University announces that this guy, Professor Thurler, Kim Thurler, has developed silk screws, okay? He has these little silkworms in his lab, and they're just working day and night to make silk. And he's been trying to get them to make screws, but in fact they don't do that for him. They just make silk fibers. But it turns out, when we come to material selection, another externality, particularly in medical materials, is in the early 1970s, Congress passed the law enacting the Food and Drug Act at the time, and they said, we will grandfather any material that's already been used as an implant in the human body. But if you're going to bring in a new material, since we're dealing with humans here, we're going to make you qualify it. And since then, to my knowledge, there has never been another material qualified for use in the human body other than the materials that existed before the 1970s. Because no one wants to spend the hundreds of millions of dollars in all the dog studies and then a human study. And so we have things like polylactic acid is one of the polymers that you can use in the human body. Well, why do they do that? Well, it's just made out of milk byproduct, okay? Okay, so yeah, you can, you know, it's not going to be toxic. And they've been using polylactic acid. So the medical folks have this big millstone around their neck when it comes to material selection, if it's going to be implanted in the body. They can use stainless steel, they can use titanium, they can use molybdenum, you know, they can use platinum, okay, because these things were used before, okay? But you can only use things. No one wants to bite the bullet and come out with a new material, okay? So they have to work with what they have. But silk was used, and they made silk screws. And one of the advantages of silk screws is they're not too stiff. One of the biggest problems we have with medical implants, you break a bone really, really badly, and they go in, they put a metal plate, could be titanium, could be stainless, and they screw it together with titanium or stainless screws. You don't mix metals because they tend to create galvanic corrosion. They're stiff and unyielding. Compared to the bone, bone's got a modulus it's not on here, but bone is probably down in this range, down here. You'd like to have something of the same modulus, because a high modulus material next to a low modulus material in a structure gives you a stress concentration. Not because of a notch, but just because of the differences in the materials. If I have a composite material with two different, very different moduluses, I end up with effectively a stress concentration. I get cracking and all kinds of problems. So people have known for years, metal screws as implants to screw bones together is a terrible design, but you need the strength of metals usually, okay? So then you also many times have to remove that metal. You can't always leave it in there. And so they came up with resorbable fixation devices, which is a medical term. Actually, I have a student who got a PhD here at MIT in materials, but he went on to become an MD, and he tells me that becoming an MD is nothing more than learning the vocabulary. Okay, doctors talk to each other in a different language. It sounds very fancy, like fixation devices, but if you learn what it means, It's really all very simple. Okay, they just like, you know, they want to talk about the anterior and the posterior, distal and proximal. Okay, so they learn Latin once. Big deal. Okay, but you'd like to have, they have resorbable polymers, but they've got some problems made of synthetics because they can cause inflammation and the immune system can react to them. Turns out silk is not such a big problem. Okay, and so using a natural product, and silk had been used in the body before. Okay, so anyway, so these silk screws, the first article I saw on this, which I can't remember where I saw it, it was just this weekend, basically talked about using the screws in children's jaws to, you know, kid has a fight or something, has a broken jaw or something, and they put the bones together with silk screws, and the silk screws eventually just dissolve in the body after they've done their job holding the bone together, so it will reattach. And then they just dissolve in the body, and you don't have to go in there and cut the kid's face open again and things. It matches things. If you have these different stiffness materials, you run into some problems. So let me just finish up. Well, actually, I won't finish up. It's time to quit. So on Thursday, I'll be back, and we'll talk about modulus versus cost and other material properties like strength and toughness, which are also critical to structural materials. Okay.